All right. Hey, what's up, everybody? Tuesday, April 20th, classwork and homework. We're doing section 7.2, which is tangents. Okay, tangents here. And a couple of the problems get a little messy, I think, around 17, 18, 19. Number 25, too. A little challenging in algebra 1 stuff. So anyways, I'm going to do number 17, and maybe that'll help you out with 18 and 19, potentially. And then number 25 I can do together as well, too. But I think that would be a fun one for you to do on your own. But anyways, we're looking at number 17 right here. And I remember this one. I remember this because I was just a geometry teacher a few years ago. It's my 4th year doing it, right? I'm kind of taking the freshmen. They're graduating this year, right? Going up with them in high school. But anyways, I remember seeing a diagram like this, and I'm like, what the heck am I being asked to teach? What am I being asked for, and what am I doing? So anyways, I haven't looked at this diagram this year yet. I haven't done this problem yet. So let's just see if I can talk through it maybe and think about what I'm thinking about when I'm doing a problem like this, okay? So first of all, what is this section, right? Whenever you get a problem like this, you ask yourself, what section am I in? What am I studying right now? And the answer, because you did the lesson with it, you took notes, you should know, what if I do my notes on section 7.2? Tangents, okay, tangents. So this is probably a tangent line, right? This is probably a tangent line here. And here, this is the tangent segment, okay, tangent segment here. So we have segment RS. Okay, R is a point outside the circle. S is a point of tangency. So remember, a tangent segment can be defined as a segment from a point outside of a line, coplanar, right? It's a coplanar segment to a circle, where a point outside the line is drawn to a point of tangency, or a point of tangency on a tangent line, right? Anyways, here. So it's actually kind of a harder definition to write out, and that's why it was tough on the exit ticket for a lot of folks here. But anyways, that's why I got myself a tangent segment right here, and I have circle P and I have circle Q. This is probably a common external tangent. Yes. This would be a common external tangent here because it doesn't. This external tangent wouldn't actually intersect the segment connecting both centers of the circle. So anyways, SR is a common external tangent to circle P and circle Q. QS is 6. So here, I mark it up. What do I know? I mark it up, and I probably know perpendicular things too. Right? What do I know? What can follow from what I'm given? And what can I mark up is going to help me on a problem before even reading it. So for instance, I'm given this. SR is tangent to circle P and circle Q. And right now you got to ask yourself in this section, what follows from that? What follows that? Meaning, what can I apply with this as an opening premise, an opening if, right? If I know that SR is tangent to circle P and circle Q, what do I know about tangents? What do I know about tangent? What about tangent segments, tangent lines? It doesn't matter. They're what? Compared to the radii that are drawn at their outer end. They are perpendicular, right? Perpendicular to the radii that are drawn to their outer end here. So I said radii because we have 2 radiuses here, but this radius perpendicular to its tangent line. This radius perpendicular to its tangent line. The tangent line hits at its outer end. The only tangent line actually hits, right? Or at least from this point. But anyways, perpendicular. So right triangles might have to do with this problem. I might also spy something that all these lines are coplanar. And here I have 2 lines, SP and TQ are both perpendicular to the same line. Okay, remember this one from first semester here? SP is perpendicular to TQ. So here I'm just thinking, like, what might I have to do in this problem? What could follow potentially from my diagram here, making connections, building on them and whatnot here. SP is perpendicular to TQ, and also SP is not perpendicular to TQ. SP is perpendicular to SR. This can give me another thing that I can potentially follow. But what I'm spying here is that these 2 coplanar lines are they're coplanar with this kind of transversal. They're each perpendicular to the same line. Each perpendicular to the same line. SP perpendicular to SR, and also TQ perpendicular to SR. Okay, so we had that theorem. Remember first semester when we have 2 lines that are each perpendicular to the same line, right? Each perpendicular to the same line. Therefore, okay, what could follow from that is that these 2 lines right here, SP, TQ, have got to be what? What do they appear to be? Well, we could actually prove that they got to be parallel to one another. So potentially that could help. I'm not actually really reading what we're being asked for here, but I know that those lines are parallel. Interesting, okay? So this sort of seems like it's not a midline or anything like that, but at least parallel to the third side. it might divide this proportionally. Remember that. This kind of looks like a basic proportionality theorem type problem here. Ooh, right? So many connections, different things to say, a lot of things we can get here. But anyways, let's take a look here and look a little bit further because I like problems like this. So I talk so much about them, don't I? All right, I should probably change color here. Sorry for the delay, folks. We want to get this done. Let's see. Oh, I got 6 minutes left, 6% left on my battery, so I better get done with this pretty quickly. Okay, QT is 6. Okay, TR is 8. Okay, PR is 30. Ooh, that's tricky. Why'd they give you PR, huh? Okay, PS. Okay, PS, I got to get this. That's the radius of this guy right here. Well, this is 8. This is 6. And yes, this is a good problem for you to do example-wise because this is kind of tricky right here. QT. So I know that my top triangle is similar to the bottom triangle by the basic proportionality theorem, right? Basic proportionality theorem. Remember that one, the basic proportionality theorem from chapter 5? It all fits. It all connects, right, in geometry. It's pretty neat here that this top triangle, because if I have a triangle where one line that connects two sides of the triangle is parallel to the third side, I would know that this segment QT divides this proportionally, right? Divides it proportionally. And I also know it creates this top triangle here is similar to the larger triangle here, right? So here I have triangle RPQ similar to triangle RQT. And I know this. We know this. Who knows this? We know it. I know this because angle R congruent to angle R. Angle RPQ, right? RPQ, this angle right here, this angle right here, congruent because they are corresponding angles that are cut by a transversal and parallel lines. So I know that these are similar by AA. So I'm thinking maybe that'll help me on this problem here, okay? So this is 8, TR is 8, this is 6, this is 30, this is then a little bit tricky, isn't it? Right? Isn't it here? So maybe what we need to do is we perhaps need to get what this is here. This is X, okay? And then this is 30 minus X. Although this actually isn't really going to help us here. Oh, I see it. This is a tricky problem. So we're not going to do the X and 3 minus X thing here. Look, I have 6. I have this radius. I have this radius here is 6. Okay, so I have this radius here is 6, and that's going to help me. Is it going to help me? Oh, man, is Mr. Fortin stuck on this? Let's see here. 6 is QT. 8 is TR. PR is 30. Okay, 30. And that's the radius here. This is radius goes over here. This is messy. This is messy right now, isn't it? Am I given this? I'm not. Oh, Pythagorean theorem. There we go. Look, there's a right triangle right here. I can actually solve for this here. Look, check it out here. Let's let this one be X. Look, I have Pythagorean theorem. There it is. Boom. Great. This is awesome. It's awesome if you get it, huh? It's super frustrating if you don't. I was about to not get it too, my friends. Let's check it out here. So here's Pythagorean theorem here. Look, I got 2 legs, and I got a hypotenuse right here. Yeah, we found it. This is good. That's why I include these challenging problems, because they're fun when you get. I know, and a lot of times you feel like you don't get them. But anyways, 36 plus 64 equals 100. Take the square root of both sides. There we go. This is going to be 10. QR is 10 right there, my friends. So we don't need that here, but we can get PQ. PQ is then going to have to be 20, right? Because 10 plus 20 equals this 30 that we have here. There we go. Fill it in. We get 20 for PQ. PS, okay, PS is going to be the radius here. Maybe we get scale factor. We got to use scale factor here. Oh, neat. Okay, so this means that, well, from this thing here to this side of this trapezoid that's actually right here, this is a 1-to-2 ratio, okay? So ST here, 8 times 2, it's basic proportionality theorem, right? This segment here is parallel to that segment, so it's dividing this triangle up proportionally, so that means this is a 1-to-2 ratio, this isn't a 1-to-2 ratio, so this has got to be 16, okay? ST is 16. Oh, man, this is a great problem. Great problem. I love it. Challenging, and man, I'm guessing a lot of folks really going to struggle with this one here. Okay, last step is to figure out what PS has got to be, and here I'm going to use similarity to do that. Right, I'm going to use similarity to do that. Check it out here. That's where you're always going to use similarity when you're dealing with the parallel lines within the basic proportionality theorem. Okay, why you do that? Well, this is the bottom of this top triangle. This is the bottom of this bottom triangle, like the large triangle here. So here we want to go small triangle. Right? We want to go small triangle to large triangle, okay? Way we can get the scale factor of that is to do small triangle. Well, here is 10, right? QR, okay? QR here is 10, okay? QR equals 10 right here. And then, so then we can compare it to TR. Wait, no, not TR. We want to compare QR. Okay, wait, yeah, QR is right here. And we want to compare it. Did I write this down? RQT. This is the same thing. RPQ. Oh, RPS is what I meant to put here. RPS is what I meant to put here. Whoops. RPS. Okay, RPS. So SR. Sorry, it's getting a little messy. Yes. Well, again, we can do it that way. SR. Okay, SR here is 24. Okay, and RT. Yes, here we go. So we're going large is 24 here. Okay, and I could have done it over here. Could have been easier to show down here. That's what I meant to do, but I realized I wrote this wrong. Okay, 24 for RS, and then that corresponds to RT over here, which is 8. Okay, so we're in a 1:3 ratio. Okay, 1:3. Small triangle is in an 8:24 ratio, and here we got 10:30, right? 1:3 ratio. Small triangle to the large. Right? Remember, the large triangle is the whole thing here. Okay, 1:3 ratio here. So we have a scale factor that's 1:3. So what's that going to tell us? If this is 6, okay, if our small is 6, what's our large going to be? Well, 6/18 is how you do 1/3. Okay, so there it is. There's my radius. My radius is 18 right there. Okay, so there's number 17. Got that one filmed. This is a long enough video. Complicated problem, right? Complicated problem for sure. Hopefully you saw it. Message me any questions. I'm guessing, whoa, this was pretty tough, but hey, geometry. Yeah, it is what it is. You gotta love this, or at least work to love it. Get it? I didn't like this until I was an adult, to be honest here. Message me if you have any questions. Have a great rest of your Tuesday. And watch the video on number 25 if you want to. Bye.